Hello, everyone. So it's a great honor and to have Professor Tim Barfoot and to provide a talk, Learning Perception Components for Long-Term Path Following. And Professor Tim Barfoot, he's from the University of Toronto Robotics Institute and work in the area of the autonomy for mobile robots, targeting for a variety of applications. Professor Tim Barfoot is an IEEE Fellow and has received 2 papers awards at the IEEE International Conference. And he sits in the Editorial Boards for the IJRR and the Field Robotics and the Foundation Board for the Robotics. So let's welcome to the Professor Tim Barfoot to have an excellent talk for us. So Professor Tim Barfoot, I think you can go ahead.
Okay, great. Well, thanks so much to the organizers for the invitation, and I'm sorry I couldn't be with you there in Paris. Unfortunately, I'm here in Detroit attending the IROS conference this week. It's unfortunate that it was at the same time. So today I did want to talk about a collection of projects related to learning different perception components for long-term path following. So let's jump right in since we don't have so much time. So what is path following? From my perspective, path following has to do with having a mobile robot first be driven through an environment where it builds a map, and then the idea is that it should try to drive through that path again autonomously. So this is just a video from several years ago where we have a robot navigating completely using vision. It's driving a path that it was previously taught, and now you can see that it's driving exactly in its tracks. And there's a lot of different applications that this can enable. The hope is that we can do this in any kind of environment, particularly unstructured environments where we don't have a lot of easy man-made infrastructure to rely on. As I said, we drive the path and then we try to repeat it. We'd like the implementation to be pretty efficient, so not relying on a lot of compute or a huge number of sensors. And we'd like it to only sort of have one training example of the path before it's able to start repeating. We might not want to rely on GPS. Here, we're not relying on it. We're also not relying on IMU. In this basic version from many years ago, we didn't even have DNNs, or we didn't even have a global map and no semantics or structure. And then the nice thing is that we can actually teach lots of these different paths, kind of like over here on the left, and interconnect them. And then we can compose those paths into different routes that weren't exactly the combinations at training time. So it's composable. And then this is kind of also just a nice framework for doing lifelong learning. And so some of the projects I'll talk about today will exploit the fact that we can drive these paths many times and build up data sets and then try to learn improved components, perception components in particular, that will help to deal with some difficult issues. So anyone who's done path following problems or any mobile robot navigation outside kind of realize that vision gets pretty difficult pretty quickly when the scene can change significantly from when you build the map until when you're repeating these paths. And so this slide just indicates some of the main issues that we've tried to deal with over the years. Lighting is sort of the one that comes to the fore right away. You know, you might teach in daytime and then want to be repeating at night. So here's an example of us driving at night with headlights on. Of course, LiDAR and radar are less affected by this, but cameras have some advantages still due to their passive nature, low power, and low costs. So there's still some advantage to trying to deal with cameras. A little bit further into the time frame, weather starts to become an issue. So and seasonal change. So here's an example of a robot driving in the winter, and you might like to teach the path, say in the summer, and then still be repeating that route in the winter. So that's another challenge that we can start to deal with. And then finally, there's of course the obvious thing of just obstructions on the path. So you can't really guarantee that just because you taught the robot a path that was obstruction free, that when it goes to repeat, it's got no obstructions. So you might like to be able to avoid obstacles while following paths. So in this talk, this is sort of my outline of the talk. I'm just going to talk about a collection of different projects over the last 2 or 3 years where we've been learning specific components within that overall pipeline that I just demonstrated in the first video. Everything from learning LiDAR and radar features for odometry, learning camera features for localization so we can match daytime to nighttime, learning a radar distraction mask so we can know what to pay attention to in noisy radar data, and then learning a change detector that will help us detect where obstacles are so that we can avoid them on paths. So let's jump into the first one, which is learning LiDAR and radar features for odometry. So a theme in this talk is basically that I'm not trying to learn everything end to end. Of course, that's one end of a spectrum. The other end is that we don't learn anything. We just handcraft all of our algorithms like we did about 10 years ago. And I guess in this talk, we're trying to sit somewhere in the middle where perhaps we're learning these front-end features, but then still combining those with quote unquote classic state estimation tools in the back end for doing things like odometry and localization. So that's kind of what we're trying to do with all of these projects today. So let's talk about this first one, learning LiDAR and radar features for odometry. And so this actually builds on an earlier paper that we put out a couple of years ago that's indicated in the bottom right here called Exactly Sparse Gaussian Inference with application to derivative-free batch nonlinear state estimation. And it's basically a technique for being able to simultaneously do state estimation, but also do parameter learning. And so we've exploited this to try to learn features for LiDAR and radar odometry. And it actually builds on the idea of expectation maximization. And so the way it works is in the E step, we take some, say, LiDAR scans in a mini batch. We do a forward pass through a network that's able to extract, in a differentiable way, of course, a number of interesting key points, covariances, and descriptors for those key points. We then match these features across time, and we build them into a differentiable factor that we put into a larger factor graph state estimation problem. We can then actually also add in other sensors that have nothing to do with the learning problem. So maybe we have some wheel odometry or some IMU data that we want to put in. And the interesting point with this framework is that our state estimator does not have to be differentiable. So in the forward pass, we're just sort of going in the forward direction and doing inference, our network's outputting features, and then we're trying to estimate our motion. But this part doesn't have to be differentiable. In the M step, we hold the distribution over the trajectories fixed, and then we just use standard deep learning tools and we back propagate back through the network to try to improve the features that we've been learning. And we just go back and forth between the E step and the M step until we get convergence. And as a video, we can look at this thing over here on the left. This is actually training. So what you're seeing are the iterations of training. And you can see at the beginning, we have randomly initialized weights, and the features that we're trying to use are really poor. But as we try to improve the trajectory and then improve the features and keep going back and forth between those, we're actually able to eventually unfold this and estimate a pretty good trajectory with fairly useful features. And I should mention we're doing this completely unsupervised, so there's no ground truth of any kind. And then here's a video at test time where you can see the features. We're estimating the trajectory. It's nice and smooth. And because we did this in this non-differentiable way for the trajectory part, we have a very fancy state estimator that's doing continuous time state estimation. It's got smoothing factors, all kinds of stuff that would be hard to make differentiable. But this tool is able to let us do that. And it's not the best LiDAR odometry in the world, but it's comparable, I guess, to some of the state-of-the-art tools. And I thought that was kind of neat that we can do that completely unsupervised and learn features. So switching gears, I'm moving on to the second project in my outline now, where now we're talking about learning camera features for long-term localization. So perhaps we want to build a map in one condition and then drive the route in another condition, and we want to be able to match these things directly. So this time we put these into a pipeline where we again use a network to output features, scores, and descriptors. We match those in a differentiable way. We then put them back through the inverse stereo camera model to produce Euclidean features, which we then align using a differentiable, this time, pose estimator. So this is a differentiable implementation of SVD, and that outputs the pose. So this time we're going to do this problem semi-supervised. And by that, what I mean is we have some ground truth on the pose, but not on the features themselves. So the idea is we're only really learning this part, and the rest of this pipeline is known and differentiable. And we get ground truth labels through another algorithm. You can ask me that in a question later if you want, but an older algorithm that's able to produce pose in a completely unlearned way, but it's kind of expensive. So we get these labels, and then we just back propagate through the whole pipeline. And we only really keep this part. So this is really just a test fixture that lets us do the learning problem. We can then take these features and put them into a fancier state estimator that we run online, where we can do filtering and things like that. So we don't need to use this very simple pose estimator when we're actually running this on the robot. And so to train these features, you need a lot of data. So we gathered some data, or took a data set that we gathered way back in 2016 that had a lot of lighting and weather variation. And we were able to train these features and then deploy them in our larger software framework on the real robot a couple of years ago. And so we drove a much larger path in the area in which we gathered the data for feature training. And here's sort of a qualitative view of how well those features are doing. This video on the left is the main story. So these little red dots are features that are matching back to a map that was built at around noon on a sunny day. And you can see where, as the video is switching, these are different conditions under which we're then testing the features and matching them back to that sunny day. So right now, this is nighttime, and we're matching these features back to daytime directly. And it's good enough that this robot's actually driving autonomously. So this is not just data set testing, but the output of closed loop localization running on a robot. And a little more quantitatively, we can see here that we taught the path at noon, and we tested at a lot of different times. You can see as a proxy of how well the localization is doing, you can see the number of features that are being matched at these different times of day as we move further from the time at which the map was built. And we still have lots of features. This is sort of at the nighttime, like before the sun comes up. You can see there are less features, but there's still enough that the robot can drive in closed loop. And we actually did that 100% successfully across this lighting experiment with only 4 centimeters deviation with respect to the path. We did this experiment even over a longer period of time, over multiple months. And eventually the features that we learned weren't able to match all the way back to the very beginning, but it's a huge improvement over what we were able to do before we were learning these things. So they sort of last for months now instead of hours. And then you might ask, well, do you need to do that semi-supervised? In fact, no, we can take the expectation maximization framework that I talked about for the LiDAR features earlier, and we can try that out on the camera features as well. And so in this case, we were able to do completely unsupervised learning of these camera features. And due to a couple of other changes in our architecture, particularly that we switched to using a pre-trained network, our unsupervised features even beat the semi-supervised features that I just told you about. And you can see over a number of different lighting conditions that we were able to get. This sort of color here is the best that we're doing. And that's completely unsupervised feature learning. So that was presented at ICRA earlier this year. And then even one step further, we had a paper that was just presented here at IROS yesterday, where we were not only just learning features, we were in addition learning an image style transfer network that was able to take the appearance of the map scene or the live scene, doesn't matter which one. I think it was the map scene in this case. So you can see a nighttime map, and we were trying to transform that into a condition that looked like the live images. So we're trying to make it look like daytime images. And so using this combination of style transfer and feature learning together in a single pipeline, we were able to back propagate through this whole thing and learn even better features or a better feature matching technique, I guess, than we were able to do with just the features alone. And I think this picture is quite interesting. So on the left, we have the output of our network just before the softmax layer where we output the features. You can kind of see what it's firing on. Blue is it's more interested in things that are blue and less interested in things that are green. And you can see if you're just using feature learning, you're sort of still firing on a lot of this low-level texture. But once we do the style transfer and the feature learning together, I think it's quite interesting that now our feature detector is firing more on key interesting landmarks in the scene. And you can see it's picking out the poles in a fence or these pylons that are sitting here. So that's actually quite a qualitative difference in what we're able to learn by adding in this style transfer network. And the bottom line is that our localization is quite excellent now with this combination of these two things. We're getting down to just a couple of centimeters of error compared to ground truth from our imagery. So localizing with respect to the path that we want to drive, we know where we are within a couple of centimeters now. So that's a huge improvement over what we were able to do a couple of years ago. Switching gears again to the third project on my outline, I'm going to talk now about using radar for localization. So perhaps we've driven a route and we built now a car in a city, and we built a route map of that route using LiDAR, and we want to localize against it using radar. And you can kind of see in this video what the output of our imaging radar sensor looks like. It's a 360-degree sweep, but you can see there's a lot of artifacts. There's a lot of strange effects that come along with radar that make it a bit difficult to work with. So what we wanted to do in this project is learn a distractor mask. Basically, we'd like to learn what to ignore and see if we could learn to ignore the things that aren't real effects in these scans. And so again, we built a network that can do this. So we take the raw radar scan, we try to put it through a network that learns a weight mask. So it's trying to learn like a weight that classifies every pixel in this scanning image as to whether it's a good thing to pay attention to or not. We then extract our actual features, and then we apply the weights to every pixel so that we get this weighted point cloud coming out of our radar scan. And then we match that to the LiDAR map that we built previously using a differentiable version of the iterative closest point algorithm. And then the idea is that we can just back propagate through this whole thing to learn this distractor mask network. And it turns out that we can do that. So our network tends to learn to pay attention to things that are closer to the vehicle. Oh, by the way, we tested that on this data set called Boreas that we put out last year. So that's free for everyone to use. There's nice benchmarking tools for doing radar and LiDAR odometry. So we use some data from that for testing. And you can see that here are some examples on these two rows of distractor masks that our network has learned. So these are the raw radar scans, and then this is sort of like more like what we're actually using for localization. And the result of learning this distractor mask is that we can cut our errors basically approximately in half. So this is before we add the distractor mask, and this is after. And you can see we're down to sort of 12, 15 centimeters error. And that's just on one radar scan. So if we put these in combination into like a fancier state estimator online, rather than just one scan, so that we're doing filtering and smoothing, we can actually do quite a bit better than that. But that's just the results on a single scan. So that's working reasonably well. And then the last project I wanted to talk about is the idea of now heading towards the idea of obstacle avoidance while path following. And anyone that's done testing off-road and trying to detect obstacles, it's pretty difficult. When you're in a more urban environment with a flat ground, segmenting out obstacles is not so difficult. But once you start to head into tall grasses and trees and things like that, detecting obstacles is actually pretty hard. So we don't try to detect obstacles. What we try to do is change detection. So because we've driven the route and we built up maps previously, all we try to do is try to figure out what's different in the live scans from the map. And in this case, we're going to be using a LiDAR to do this change detection. So here's just a cartoon. We want the robot, it's supposed to follow this purple path, but there's somebody standing on it. And so we want to deviate around that. So we need to detect this change. This person will look like a change compared to the map that we built when we taught the route. So to do that, we actually use range images from our LiDAR. We compare the range images to each other. We then put the differences into a neural network that's hopefully going to try to find these changes. We use a number of different losses to encourage the network to find changes, to not find too many changes, and to make those changes consistent over time. And so our loss is built from those three things, and it's done completely unsupervised. So there's no ground truth labels that we use in the learning. And by gathering a bunch of data just from the robot without any ground truth, we're able to learn a network that can do this change detection. And this video is kind of showing what that looks like. This is what the point cloud from the LiDAR looks like. And then this is what the change detection is looking like. And you can see this little green person here. So to evaluate this, what we did was we covered one of our grad students with this retroreflective suit, which is very easy to segment out from the scene so that we can have some ground truth labels. And then that was showing earlier like that we could detect those changes pretty reliably. And so again, now we're putting that in closed loop on this robot. It's driving around a path, and you can see that it's able to detect the changes and then make small deviations to its long-term route to avoid those obstacles while still following the long-range path. So That's sort of a work in progress. You can see we're testing still on fairly easy scenarios, but we did do some testing, as you saw in the previous video, where we're in tall grass and amongst trees and things like that. Oh yeah, this part of the video. And it's working better than sort of the naive baseline of just comparing the closeness, the nearest neighbor closeness of points to the map. That produces a lot of artifacts that we don't really want to, a lot of false positives in particular. So this network is much better at not getting false positives than the naive baseline. So that's my talk for today. I just wanted to keep it fairly short. I know you've got a short timeline. Just thanks to all the students and collaborators that have done the work and the sponsors. And I'll just leave you with a few summary thoughts and questions on this slide. So I would say after a few years of working on these things, learning is definitely letting us do things that we couldn't do before, particularly matching daytime to nighttime. Wouldn't have dreamed that that was possible 5 years ago. Unsupervised and semi-supervised learning, I think, still benefit quite a lot from using classic state estimation tools in supporting roles, either through labeling data sets or providing context for learning. And so, related to the context is that although we may not want to learn the entire pipeline end to end, we might want to train it end to end so that we can learn, say, features that are useful for the actual tasks that we're interested in, like localization. So being able to backpropagate through a state estimator is very useful. And then just to make the counterpoint, we don't always have to actually make the state estimator differentiable. I think we could either learn something using a simpler state estimator that is differentiable and then deploy, say, the features in a more sophisticated estimator, as we did in a few examples in this talk. Or we could use this other framework that I mentioned that uses expectation maximization and a state estimator that's not differentiable to learn features. And then I would just leave you guys with one final thought, which is that I think it's tempting to just sort of crank data sets these days. There's a lot of them out there, but I really think there's value still in deploying what you've learned on real robots and trying to validate that what you've learned is actually useful for the original task. So all of the talks, all the things I showed you today, we deployed on real robots to really make sure that the things we were learning are actually useful. So I think I'll leave it there, and happy to take any questions if there's time.
Thanks, Professor. Thanks for sharing these insightful.
Sorry, I can't really hear you.
Does anyone have problems with questions? Oh, actually, you have a question. Can you hear me?
Yeah, I don't really hear what you're saying. You might have to move closer to your microphone.
So can you hear me, Professor Tim Barfoot?
Yep, much better. Yep.
Okay, cool. So does anyone has questions? Okay.
Hi, Tim. Can I ask, adding the LiDAR safety layer, how do you think about that, given that with visual teach and repeat, it's typically assumed that the safety comes from following the same route?
I think that's Morris. I can't quite see. It sounds like you. I don't quite understand the question. Which LiDAR safety layer are you speaking about?
So previously with visual teach and repeat, you're precisely trying to follow the same trajectory, which kind of defines the safety case for the system. With this deviation based off of LiDAR, how do you think about the safety case in that situation?
Yeah, that's a good question. We've been thinking about that a little bit. I guess our answer right now is that when we teach the path, we're exploiting some human knowledge there to define the path. Our hope and what we do in our interface right now is we have the human also define a corridor around the path for which the human at teach time believes that the path is safe. So you could imagine like a 2-meter corridor either side of the path. And the human is saying, I think if you stay in this 2-meter either side of the path corridor, you're going to be fine. So then if that's true, which may or may not be true, but let's say that that's true, then all we have to do is detect changes and try to avoid them. So as long as we stay within that corridor. So our path planner is actually BitStar. I don't know if you know that algorithm, but we're using BitStar to avoid these obstacles. But BitStar then gets this corridor constraint so that it has to stay within the 2-meter corridor that was given to the algorithm. That's the answer we have so far. So the human is again sort of deciding where the safe corridor is up front.
Okay, thanks very much.
Okay, does anyone has other questions? Okay, thanks for the Professor Kim Barfoot, and it's a very great talk.